All right, so we've been talking about proportions. Proportions have to do with categorical data, though. So if you have categories, you find the proportion of something. So like with the M&Ms, we found the proportion of orange, so that's a category. But what about quantitative data? If you have quantitative data, you can't find a proportion. But you can find a mean. So we're stepping away from sampling distribution models for proportions and moving towards sampling distribution models for means. They're similar, but they're not the exact same. First of all, if you read last night, you were talking about this dice averaging thing. So it says the dice simulation may look like a special situation, but it turns out that we can solve the dice. What we solve the dice is true for means of repeated samples for almost every situation. All right, that's nice. Awesome. So the sampling distribution of any mean becomes more nearly normal as the sample size grows. We saw that yesterday with proportions. And all we need is for the observations to be independent and collected with randomization. We don't even care about the shape of the population distribution. We're really only worried about a sample distribution that is somewhere, sometime. So we call that the central limit theorem. The mean of a random sample is a random variable whose sampling distribution can be approximated by a normal model. So look, we're not really worried about some sample. The larger the sample, the better the approximation will be. That makes sense. Okay, that's not anything fancy. They call it a fancy name, but it's not that fancy. We kind of saw that with proportions. They alluded to that with proportions. They just don't really call it that. Okay? With a sampling distribution model, there are assumptions and conditions. They're almost the exact same. We have independence. So the sample values must be independent of each other. We have sample size. Sample size must be sufficiently large. We have randomization that backs up independence. Somehow sampled randomly. 10%. N has to be less than 10% of the population. It backs up independence. Now, here's the last part, and here's the worst part. When we had proportions, we could do expected values, expected successes, expected failures, right? So we have success failure greater than or equal to 10. There's a concrete number, great, wonderful. Which means we don't have that anymore. All right, we don't have a P, so we can't do that. So, although the CLT tells us that a normal model is useful in thinking about the behavior of sample means when the sample size is large enough, it doesn't tell us how large a sample we need. The truth is, it depends. There's no one-size-fits-all sample or size. If the population is unimodal and symmetric, then a fairly small sample will suffice. If the population is strongly skewed, then you're going to need a way larger sample to suffice. Okay? So think about it. Let's say we think about coin flips. We said that yesterday. Well, you can't have means with that, though, so we can't do that. We have some scenario where we have this perfectly unimodal and symmetric distribution. We did the sample anyway. No. Then we can, any sample size will work because it was unimodal and symmetric to begin with. Then they allude to the CEOs in chapter 5, which we kind of talked about. But if you think about CEOs, there are a lot of CEOs that make really great salaries. And there's some CEOs that make like crazy large salaries, right? And so we look at that histogram, it was skewed to the right. Because there was people with large salaries and then even larger and larger and larger. There's outliers and things. That sample then isn't initially unimodal and symmetric. So we're going to need a rather large sample size for us to be able to make a normal model. Okay? We're going to see that in the question we're going to do and on your homework question. All right? In AP statistics world, generally speaking, a sample size of 30 is large enough. But that's not always, I mean, sometimes a sample size of 2 is fine. But generally 30 is large enough. But this is the crux here. You'll just need to think about the sample size in the context of what you know about the population and then tell whether you believe the large enough sample condition has been met. It's kind of up to what it looks like to begin with. What do you picture? So we're going to go through some examples. We're going to hopefully differentiate some things. What you need to know, though, is some things to define the sampling distribution. So we already talked about that the mean of the sampling distribution is the mean of your sample. Okay? Yeah? But the standard deviation, we had that weird formula yesterday for proportions. Now we have a new one for means. The standard deviation of the population divided by the square root of n. Okay? No. You're going to know n. So you find n by the square root, you find a number. There's no rational. Yeah, the mean is like what they're giving you. It's going to be a sample mean, so it's going to be like an X bar. On the AP Stats formula sheet, yesterday I said, oh, look, there's a standard deviation for sample proportion. Look, the one above it says sample mean. So you don't have to remember the standard deviations. The means should be easy to figure out. Standard deviations, you're going to find there's lots of stuff going on. There's when you do all these different hypothesis tests and things. And so there's lots of things to keep track of. So they're all in there for you. Okay? So you don't have to memorize that. You'll use it enough, you'll know kind of what it is, but you don't have to memorize it. That's nice for when you have a moment on the AP exam and you're like, what? Oh, yeah, formula sheet. Okay. So, there is a question in your book. It's number 29 that I'm not doing, but this alludes to 29. So I have all the pictures and everything necessary that we will need to talk about it, okay? It says, researchers measured the waist sizes of 250 men in a study on body fat. The true mean and standard deviation of the waist sizes for the 250 men are 36.33 and 4.019 inches, respectively. Here was the histogram of that sample of 250 men. Okay? What do you notice about that just to begin with? It's unimodal and pretty symmetric, right? That means that probably most of our sample sizes are going to be okay because the original information was unimodal and symmetric. All right? Anyway, in exercise 29, you looked at the histograms of simulations that drew samples of size 2, 5, 10, and 20. And the summary statistics for these simulations were as follows. So we have these 4 histograms, different sample sizes. This is size 2, this is size 5, 10, and 20. And what do you notice about those histograms? They're unimodal, and they're getting more symmetric. The first one might be a little bit skewed to the right, maybe just a tad bit, but then they get more symmetric as the sample size increases, right? Okay. Now, these are all the means and standard deviations of those sampling distribution models. We want to match that up, or with those simulations. We want to match that up with what we would expect from our model, okay? So, on A, according to the central limit theorem, what should the theoretical mean and standard deviation be for each of these sample sizes? What should the mean be for everything? Yeah, 36.33 for all of them. That should be approximately where the mean should be. What about the standard deviation? It would change, so what would I do to find that? Yeah, so 4.019 divided by the square root of n, so here it's 2, and then here it's 5, and here it's 10, and 20, right? Okay, and so those numbers, I have them calculated already, are 2.84, 1.797, 1.271, and 0.899. Are you surprised to see the standard deviation decreases? You shouldn't be, because standard deviation decreased yesterday, right? As your sample size increased, your standard deviation decreased. Okay, so we have found everything they want us to find in part A. In part B, it says, how close are the theoretical values to what was observed in the simulation? So for the means, how close are they? Pretty close, especially these two. Like they're almost like right on it. What about the standard deviations? Again, not really close, especially that one, right? Which again backs up that CLT, that the larger your sample size is, the closer that your samples distribution model is it's gonna get closer to the sampling distribution model. All right, yeah. Okay, closer to a normal model. So, looking at the histograms in exercise 29, which I have down here. At what sample size would you be comfortable using the normal model as an approximation of the sampling distribution? So, on which one of these, are all of them, or which ones would you say it would be appropriate to use a normal model? Definitely sample size 20, right? It's unimodal and symmetric. Definitely sample size 10. That's unimodal and symmetric, right? What about sample size 5? I'd be okay with that. It looks unimodal and symmetric to me. And then sample size 2, I'd be cautious. It's a little bit, but I mean, it's just that much skewed that I'm like, all the rest of them look so nice that I'm like, I don't know. So I said I would be comfortable using the normal model as an approximation for sample size 5, 10, or 20. So again, it's all based on what this original histogram looks like. This was a little bit skewed to begin with, right? But it was unimodal, roughly symmetric, so your sample size didn't have to be too large. On your homework question that you're going to have like this, you're going to have to go back and look at number 30, okay? On number 30, your original histogram isn't pretty like this. Your original histogram is skewed. If the original histogram is skewed, what do you think is going to happen for these types of sample sizes? It's going to still be skewed, and then it's going to get to where it gets normal. They're not all going to look as pretty as these, right? What do you think is going to happen when you start comparing this table to what you would expect? If you had originally had the skewed distribution and it's going to be skewed for a little bit and get more normal, are you going to expect all of these to be so close like they were here? No. And it's because the sample size was so small. All right? This goes back to that big idea that if you can kind of picture what it should look like to begin with anyway, then you should be able to determine what kind of sample sizes are appropriate. Here, small sample sizes were appropriate. On your homework, maybe small sample sizes aren't appropriate. Okay? Yes? Does that make a little bit of sense? And then on part D, what about the shape of the distribution of waist size explains your choice of sample size in part C? We've talked about that a lot. What shape are these making? Unimodal and symmetric. They're making these nice looking normal model type things, right? So just be thinking about, if it means, that's the hard part, to think about what it's going to look like to begin with, to see if you can actually use a normal model. There's no right way to do like success, failure, or anything. You have to kind of pick it out. It's not like proportions. So let's actually do some actual things. I'm just going to talk about 33 real fast, and then we can do other stuff. I'm not going to actually do 33. A college's data about the incoming freshmen indicates that the mean of their high school GPAs was 3.4, with a standard deviation of 0.35. The distribution was roughly mound-shaped and only slightly skewed. The students are randomly assigned to freshman writing seminars in groups of 25. What might the mean GPA of one of these seminar groups be? What should the mean GPA of one of the seminar groups be? 3.4, right? No big deal. Describe the appropriate sampling distribution model, the shape, center, and spread with attention to assumptions and conditions, and make a sketch using the 68, 95, 99.7 rule. All right, so you would find the standard deviation, right? It would be 0.35 divided by the square root of 25, right? You would draw it all out like you did last night. No big deal. Label it 68, 95, 99.7. Yeah, check the conditions. They're all very similar, except for the last one, so let's talk about it. Large enough. We don't actually have a histogram this time to look at, okay? But we do have a mean and standard deviation for the incoming freshmen, right? If the mean GPA for incoming freshmen is 3.4, do you think this is like a really super prestigious school? No. So that means I'm not going to see this really skewed to the left distribution with like everyone gets a 4.0 and stuff. Like that's not what I'm looking. I'm not going to see that. If it's 3.4, it's probably like a nice university, but it doesn't have like really strenuous entrance requirements, yada yada, right? So you're going to have a lot of people around 3.4, people that are above, people that are below, right? It's going to be unimodal and probably roughly symmetric. So 25 is probably large enough. Okay? Now, if it had said the mean GPA was 3.9 with a standard deviation of 0.002, that's probably not going to be unimodal and symmetric. That's probably like super prestigious school, or like everyone needs to have super high grades, right? And maybe it's going to be skewed, and so then you wouldn't want a sample size of 25. You want a sample size of 50, 60, 75, something, right? That counteracts that skewness. So that's the hard part about this. You have to kind of picture it in your head first, okay? All right, let's do 37 and 39, and then I'll be done. Assume that the duration of human pregnancies can be described by a normal model with mean of 266 days and a standard deviation of 16 days. Okay? Information, good to know. What do you not have at this very moment? We have a mean and standard deviation, but what are we missing? We're not talking about proportions, we're talking about means, so we don't need a proportion. We don't have any sample size, right? So we're not talking about a sampling distribution yet, because we don't know the sample sizes, right? So on part A, it says what percentage of pregnancies should last between 270 and 280 days. That has nothing to do with sampling distribution models. That's just asking you, they're saying, hey, it's a normal model, and here's the mean, and here's the standard deviation. Find me a percentage. I could have given you that question in chapter 6. Okay? So not everything has to be a sampling distribution model. If you don't have that information, it's not it. That's not what we're talking about. Okay? So how do you figure out part A? Normal CDF. And what's your lower boundary? 270, and your upper boundary is, and your mean is, and your standard deviation is, and you should get 0.211, so 21.1% of pregnancies last between that 270 and 280 days. Right? That does not have anything to do with sampling distribution. On part B, at least how many days should the longest 25% of all pregnancies last? Again, no sample size. We're not talking about a sampling distribution model. We're just talking about answering this question about a normal model. So if they give you a percentage, what did we do? Inverse norm. Now, it says the longest 25%, so why was that tricky? Right. The calculator for inverse norm, it reads, it asks for an area, and it's asking for the area under the curve. It reads from left to right. So it's reading an area from here to here. So the highest or longest 25% is this 25% up here. So that means this number is 75% of all the data. So make sure you use 75%. So it's 0.75 with the same mean and standard deviation. So that is, I got 276.8 days. So A and B were just normal model questions. Yeah? Okay. On C, suppose a certain obstetrician is currently providing prenatal care to 60 pregnant women. Bingo, we have a sample size, right? Let Y bar represent the mean length of the pregnancies. According to the central limit theorem, what's the distribution of this sample mean, Y bar? Specify the model, the mean, and the standard deviation. What model would we be using here? A normal model. What would the mean be? 266. It should mirror the mean of the population described before, right? And then what about the standard deviation? Yeah, 16 divided by the square root of 60, which happens to be 2.07. Yeah? That's what I did. I specified the model, the mean, and the standard deviation. This is standard notation that says I'm using a normal model with that mean and that standard deviation. That's acceptable anywhere. Okay. On D, what's the probability that the mean duration of these patients' pregnancies will be less than 260 days? $266. Subtracting 2.07, so 263.93 is one standard deviation, right? I'm looking for less than 260. So now you should use your calculator, right? Why is that picture that I drew just important to you all? What am I trying to accomplish with that picture? I'm trying to give you guys points for your response questions. Something you should be working on. All right, so we would use our calculators. Negative infinity. What is negative infinity technically in this scenario? 0. You can't be pregnant for negative infinity days. I doubt it. 260 is your upper bound, and then 266 and 2.07. So you get a probability of 0.0019. Now, what should we have done on part C before we did part D? Because it asks you to. You should be checking conditions, right? Well, do you think that these 80 people somehow have randomness? Hopefully they're a good representation of the population. Is 60 less than 10% of all pregnant women? Yes, probably. And then, do you think 60, the sample size is large enough? What do you think? It says in the beginning that it had a normal distribution, right? So 60 should be large enough, no big deal. All right, on 39 though, it says the duration of human pregnancies may not actually follow the normal model described in exercise 37. Explain why it may be somewhat skewed to the left. Why might it be somewhat skewed to the left? We're talking about length of pregnancy, right? Some people are going to be close to their due date. Some are always going to be right after. But there are a lot more things that can happen before, right? Babies are born prematurely, right? People are born early. Complications happen, and they have to do emergency surgeries, that kind of thing, right? So there's more likely to be things that happen before, so it might be skewed to the left. Right? Eventually, you can't be pregnant forever, so it's not going to even out on the other side. Your doctor's going to be like, too bad, this baby's coming out now. Okay? So, on B, if the correct model is in fact skewed, does that change your answers to part A, B, and C of exercise 37? Explain why or why not for each. What did we do for part A and B? We just use a normal model. If it's skewed to the left, can we just use a normal model because we feel like it? No. So that would definitely change our answers to A and B because we couldn't do it. Not allowed. Would it change our answers to part C though? No, it just says it's somewhat skewed to the left. We have a sample of size 60. Hopefully that would overcome that, and you would have a sampling distribution model that was unimodal and symmetric. Okay? So that wouldn't change part C. All right. You have 4 homework problems. And I'm giving you the practice quiz, which is not due on Monday, but people wanted to start looking at it, so that's fine.
Are we going to learn new stuff on Monday?
On Monday, all we're going to do is we're going to go through, we've talked about 2 different things. I'm going to give you a variety of problems, and you need to identify if you're talking about proportions or means, so use the right thing. No. Oh, I don't know what that is.